Bismillahirrahmanirrahim. Now in this video we start with an example of uniform random variable. The phase angle theta of the signal at the input to a modem is uniformly distributed between 0 and 2 pi radians. Find the CDF, the expected value, and the variance of theta. From the problem statement, we identify the parameters of the uniform random variable as a is equal to 0 and b is equal to 2 pi because the input values are 0 to 2 pi radians. And we have to find the probability, what is the probability for of a phase angle of a signal received by the modem. So the PDF of f theta, this is capital theta, this is small theta, is equal to 1 over 2 pi minus 0 because it is 1 over b minus a, b is 2 pi, a is equal to 0, so it gives us 1 over 2 pi, and otherwise it is 0. And CDF is 0, and this is x minus a, x is theta over here as you can see, so theta minus 0 divided by b minus a, 2 pi minus 0 is equal to theta divided by 2 pi, and 1 is for all the values greater than theta greater than 2 pi. Expected value is b plus a divided by 2, so b is 2 pi plus 0 gives you 2 pi by 2, 2 and 2 are cancelled, so it is equal to pi radians. And variance is b minus a whole square divided by 12 is equal to 2 pi whole square divided by 12, so it is 4 pi square divided by 12 becomes pi square divided by 3 radian square. Exponential random variable. Exponential random variable is used to predict the amount of waiting time until the next event occurs, that is success, failure or arrival. For example, we want to predict the amount of time until the customer finishes browsing and actually purchases something in your store, the amount of time until a machine fails, the amount of time you need to wait until the bus arrives, and things like that. So we have to wait for the event to occur. The exponential distribution is one of the widely used continuous distributions. It is often used to model the time elapsed between events. X is an exponential random variable if the PDF of x is given as f of x is equal to lambda e raised to power minus lambda x. This is its PDF, and CDF is 1 minus e raised to power minus lambda x, and expected value is 1 over lambda, and variance is equal to 1 over lambda square. Lambda is an event rate which is the same as in Poisson distribution. Event rate is like the number of customers arriving at the bank in an hour, or the number of earthquakes per year, or the number of car accidents in a week. So the graph of PDF exponential random variable is like this, and if lambda is equal to 2, then the curve is like this. Lambda is equal to 1, then curve is like this, and for lambda is equal to 1 by 2, there is very little curve in the line. So we can see that the decay tends to be linear as lambda gets smaller and smaller. And CDF is given over here. So if lambda is equal to 0.5, then CDF curve is like this, and so we can see that it goes more exponentially as the rate increases, the CDF. An interesting property of the exponential distribution is that it can be viewed as a continuous analog of the geometric distribution. To see this, recall the random experiment behind the geometric distribution. You toss a coin until you observe the first head. Now suppose that the coin tosses are delta seconds apart, and in each toss the probability of success is p is equal to delta multiplied by lambda. Also suppose that delta is very small, so the coin tosses are very close together in time and the probability of success in each trial is very low. The exponential distribution is memoryless. To see this, think of an exponential random variable in the sense of tossing a lot of coins until observing the first heads. As we know that we have to see the we will stop the experiment or observation when the first success is achieved. If we toss the coin several times and do not observe a head from now on, it's like we start all over again. In other words, the failed coin tosses do not impact the distribution of waiting time from now on. The reason for this is that the coin tosses are independent. We can state this formally as p x is greater than x plus a such that x is greater than a is equal to p of x is greater than x.